Welcome to the massive open online course on Aspen Plus. Today we are going to discuss about the user-defined model in Aspen Plus. In many situations, you will find certain processes which are a bit complicated in chemical engineering domain, and they cannot be represented by any model or any block that has been already provided in the menu of Aspen Plus, whatever you find in the model palette. For instance, you find this pebble bed reactor. You might be aware that pebble bed reactors are a type of high temperature gas cooled nuclear reactor that use small spherical fuel elements, something like this, and these are called pebbles or fuel pebbles. And these pebbles are used instead of fuel rods in the nuclear reactor. Each pebble in the reactor core is a small sphere, typically of the size of a tennis ball, containing uranium dioxide or uranium and thorium in a coated form. The fuel is encased in multiple layers of ceramic, graphite, and concrete, which act as a containment barrier and increase the structural integrity of the fuel. PBR, that is the short form of pebble bed reactors, they leverage small spherical fuel elements and inert gas coolant to achieve efficient and safe high temperature nuclear generation. Their design allows for continuous fuel cycling, high thermal efficiency, and passive safety that makes them a promising option for future nuclear power generation. Now, this kind of reactors, they do not fall into any of the categories that we have learned so far, such as the CS tier or plug flow reactor or packed bed reactors. It doesn't fall in any of those categories. So basically, there need to be an option for writing your own code. That means you need to write your own code in some programming language which Aspen Plus understands and develop your own user-defined model. The next example is of a photocatalytic multi-tube reactor. A photocatalytic multi-tube reactor has this kind of configuration where a bunch of borosilicate glass tubes are bundled together and acetaldehyde is fed from one end and UVA light source is given over here to facilitate the photocatalytic reaction, and the product comes out from the outlet. When acetaldehyde is exposed to the ultraviolet light source within the wavelength of 320 to 400 nanometer, and also in presence of oxygen, then it can undergo photocatalytic reaction and generate radicals. And this radical formation may lead to secondary reactions where acetaldehyde is oxidized to acetic acid or even further to carbon dioxide and water. Again, this kind of photocatalytic multi-tube reactor is not possible to be defined within the existing list of reactor modules that Aspen Plus offers in its model palette. And the next example is of ANN model. ANN model is very common. Everybody uses ANN model for their work. Even in chemical engineering also, ANN model is extensively used. and it has set of input layer, hidden layer, output layer. The inputs are fed into the input layer and it undergoes lot of calculation inside the input, hidden and output layers, and then outputs are taken out. Basically, it's a kind of black box model where the underlying equations do not have any such physical meaning. So this ANN model is also not there in the Aspen Plus domain. So if you come across this kind of reactors or this kind of processes where such operations or activities need to be computed, there should be some kind of options in Aspen Plus where the user can write their own code in some computer language which Aspen can understand, and the entire modeling can be facilitated. Fortunately, Aspen Plus gives us the option. We will discuss it today. Now, there are various softwares used in chemical engineering. Obviously, Aspen Plus that we are currently learning, and there is MATLAB. This is also extensively used. Fortran is a very good language which is used by the engineers for decades together. Lately, Visual Basic and Python, they have been used by chemical engineers for writing certain codes. And obviously, the Microsoft Excel. Microsoft Excel is a very powerful tool for any kind of computation because Microsoft Excel has a lot of commands which are very useful to perform small calculations, and a combination of small calculations can develop a kind of model that we intend to use. Now, Aspen Plus can directly talk to Microsoft Excel and Fortran. You can write your code in Fortran and Microsoft Excel and directly attach to Aspen Plus. So Aspen Plus gives that provision to you. Further, there are other softwares like Python, Visual Basic, MATLAB, which may also be connected with Microsoft Excel. So there might be a three-way connection that we can communicate between Aspen Plus and Microsoft Excel. Microsoft Excel can be connected with MATLAB. So there may be an indirect connection between Aspen Plus and MATLAB. Or there might be an indirect connection between Aspen Plus and Python through Microsoft Excel. Similarly, there might be a connection between Aspen Plus and Visual Basic through Microsoft Excel. And if you can write a very good program in Fortran, you can directly write over here and connect to Aspen Plus. You do not need to go through the Microsoft Excel. So in today's lecture, we'll learn how to connect Aspen Plus with Microsoft Excel, and then we will learn how to connect Microsoft Excel and MATLAB, and then the three-way connection can be established. For that, let us go to the simulation window. So this is the Aspen Plus simulation window, and you will find the user models over here. In model palette, under user model, you will find 4 types of user model: user, user 2, user 3, and hierarchy. Now, if you hover over these user models, you will understand what exactly they do. The first one is user. So, unit operation defined by user supplied Fortran subroutine. As I said, that Aspen Plus can directly talk to Fortran subroutine. So, you have to use this particular block, and you can attach your Fortran subroutine with this. Second one is user 2. Here you have for supplied model with any number of inlets and outlets. Now, for user model, the first one, you can work with only a single input and single output. Whereas by user 2, you can attach any number of inlets and outlets. User 3 is to invoke a user supplied open form model, and hierarchical block, it contains the directories. Now we will skip these two things for the time being. In today's lecture, we will concentrate our work on user 2 model, that is multiple input, multiple output, and we'll learn how this user 2 model can be used to define an Excel model and how can we connect it with a MATLAB subroutine. So basically, we shall learn these three connections. So Aspen Plus to Excel, Excel to MATLAB, and then the three-way connection that we'll learn today. For that, let us take an example problem and then try to solve it using Aspen Plus and subsequently using Excel and MATLAB. So this is our example. A mixed flow of water of 200 kilomole per hour and ethanol 100 kilomole per hour at 30 degrees centigrade and atmospheric pressure is available. So we have one mixed flow, that is our feed stream. An arbitrary process, that means the process is not defined properly. Okay, we do not have any set model for this process. An arbitrary process divides the flow into two parts in 3:7 ratio. That means we have a process, we have the feed as defined, and it divides the flow in two parts, 3:7 ratio. So it is 3 parts, it's 7 parts. And then the first part is released at 51 degrees centigrade and 4 atmosphere pressure. So this part, it is released at 51 degrees centigrade and 4 atmosphere pressure, while the other part is released, that means this one, it is released at 86 degrees centigrade and 9.5 atmosphere pressure. Okay, so it is written 9.5 bar pressure, not atmosphere. So the first one is 4 atmosphere and the second part is 9.5 bar pressure. Now develop an user model in Aspen Plus using Microsoft Excel. So the first problem is we will define an user model and we will set Microsoft Excel only. Okay, so how we can use only Microsoft Excel to solve the problem. And the second problem is develop an user model in Aspen Plus using MATLAB. Okay, so we'll connect Aspen Plus with MATLAB and solve this problem. So problem is very simple. I have left it very simple so that I can explain it in a better way and you can understand. More complicated problem can be solved by yourself. So let us solve this problem first. For that, we have to go to the Aspen Plus window. First, we have to define the flows as we have ethanol and water. So we will define them in the properties. So we have ethanol and water, and then we have to define the property method. Property method has not been suggested in the problem, but we can use Peng-Robinson for ethanol water system. So it is Peng-Robinson method, and we can run. Okay, the property method has been run. We go to simulation. So in the simulation model, go to user model and choose this user 2 because we can use multiple stream. Okay, any number of inlet and any number of outlet. Now in this problem we have only single inlet. So we have only one inlet and two outlets. The process divides the flow in two parts in 3:7 ratio. Okay, so this is the first part and this is the second part. Let us rename them. Let us name them as feed, and this is product, and up, and this is product down. Okay, and this is 3:7. So if 3 parts go over there, we'll have 7 parts over here. Now first let us define feed. Feed is, let us see once again. So water 200 kilomole per hour and ethanol 100 kilomole per hour. We have the feed at 30 degrees centigrade and atmospheric pressure. So we'll define it here as 30 degrees centigrade, atmospheric pressure, and ethanol, it is 100, water 200. Okay, so ethanol 100, water 200. So very simple definition of feed. Now let us go to the block. Okay, now user 2, the B1 block has to be defined. Okay, now the user 2 subroutine. Here the user 2 subroutine has been given model. So if you have a Fortran model, you can attach over here. Okay, you can write the Fortran model name. And if you have an additional subroutine, Fortran subroutine, you can write there. But in today's lecture, we are not going to discuss about the Fortran. We'll discuss about Excel and MATLAB. And Excel file name has been given over here. Okay, Excel file name. We can browse and find the Excel. Now, we cannot just give any file name. We have a proper template for that. Okay, and I will show you where the template is found. Now, you have to go to the, so you go to the program files and let us open a new folder. So let us name the new folder as work folder. Okay, and in this work folder we will keep all our files. Now where to find the Excel template? We'll go to the program files, Aspen Tech, Aspen Plus, Engine, User, User Excel template. Okay, so there are actually two templates, user template and user Excel template 95. So 95 template is an older version, so we'll not use it. We'll use user Excel template and we shall copy this and go back to our own folder work, and there we can paste it. And we can name it as, just give a name. We will give the name as, say, my temp. Okay, so this is our Excel file name. So we have to give the address of this my temp. So you can copy the path, go to Aspen Plus, and here you can paste. So This is the Excel file name. C drive work is our folder, mytemp.xls. So we will work with this Excel file. Okay. Now you go to user array and you have to define the number of parameters. For instance, you may have to change the flow rate. Okay, here they have said that the flow rate has to be divided into 3:7 ratio. Okay, now for instance, you may in the future you may try to change it to 4:6 ratio or 7:3 ratio or 1:9 ratio. Okay, so you have the option to change it. So you may have to use these 3:7 information as a parameter so that you can change. Okay, so we may think of, say, 3 parameters. So all of them as real parameters with corresponding characters name. So we can say 3:7. So let us write 0.3. Okay, so 0.3 is the part. 3:7, it is 0.3 and another is 0.7. And we will name it as flow fraction. Okay, so 0.3 of feed will go to the product up and 0.7 of feed will go to product down. So this is a flow fraction that we have given. Now let us keep the pressure as other 2 real parameters. For instance, in the problem, pressure has been defined as 4 atmosphere and 9.5 bar for the 2 parts that will be divided. So product up will have 4 atmosphere pressure and product down will have 9.5 bar pressure. But we may want to change them to 5 atmosphere and 10 bar respectively. So we want to play around with this data. So let us keep them as real parameter. So we will set it as 4 and 9.5, and then we call them pressure of product up in atmosphere, and then pressure of product down in bar. So these are the 2 real parameters we define. And then go to the calculation options, and we always keep the bypass when flow is 0 as ticked, because as you know that these problems are not properly defined. We are defining by writing some code. So there is always a possibility that some flow will be calculated as 0. Now, you may understand that Aspen always calculates the mole fraction and all. So if the flow is 0, then something by 0 will be undefined. So all the full mole fraction calculation and other things will be undefined. So Aspen Plus will give a lot of error. So we give this option, calculation option, as bypass when flow is 0 as ticked, so that if the flow comes to 0 condition, the calculation will be bypassed. Okay. Then stream flush. We have a stream product up and product down. We will define their temperature and pressure, right? Now, instead of pressure, we can define vapor fraction, enthalpy. Instead of temperature and pressure, we can write pressure and vapor fraction also, or pressure and enthalpy also. So any combination of temperature, pressure and vapor fraction and enthalpy, you can specify the flash type, or you may not flash the stream. But as we are providing the temperature and pressure only, so we will choose this option, temperature and pressure. And the product down also, we'll use the temperature and pressure. So when we choose this temperature and pressure, then thermodynamic condition of the flash will be calculated. So we will choose this, and that way system is defined. Now our required input is complete and we are ready to run. But before that, let us open the mytemp work file. So this is the Excel file, and you will find Aspen input, Aspen output, real parameters, everything is empty. They have not been populated. So template file has sheets over here, but nothing is populated. Now it might so happen that your template file already contains something, because the person who has developed the template, they might have worked on certain problem and then they have created the template. So that might be possible. If certain data are already there, you can delete them. Okay. Otherwise, if you find the template as empty, it is absolutely okay. Now you run the process. Okay. So you run the process over here. So it runs and it gives some warnings. Okay. So check status and see what are the warnings. The following unit operation blocks are completed with warnings. So what are the warnings? It says total flow is 0. Obviously the total flow is 0 because we have not defined any model equations over there in our system. Right? I mean, we have said it's an user model and that's all. But we have to define that product up is 0.3 times of feed, or product down is this, or product up is having 51 degrees centigrade temperature. So those things we have not defined at all. So warning is total flow is 0. And as we have ticked the bypass when flow is 0, that item, so it is giving a warning. Otherwise it would have given an error. And obviously the block B1 is not in mass balance. The feed is entering, feed out we have not defined, so mass balance is not there. So these are the warnings. So let us go to the Excel file and see that feed has been populated. We have not entered, right? But Microsoft Excel has taken the data from Aspen Plus. So Aspen Plus has the input as feed. It has ethanol, water, total flow. Ethanol is 100 kilomole per hour, but Aspen Plus always throws the data in SI unit. So it will be 100 kilomole by 3600. So it will be kilomole per second. So that data will be given over here. Similarly, 300 kilomole per hour of water by 3600. So, sorry, it is 200 kilomole, right? 200 kilomole per hour water. Let us be doubly sure. Yeah, it is 200 kilomole. So 200 kilomole per hour. So per second it will be 0.555. Total it will be 300, that is 0.833. So it will be always given in SI unit. Similarly, temperature. Temperature, it is 30 degrees centigrade, right? So 30 degrees centigrade is 303.15 Kelvin. So temperature is given in Kelvin. Pressure has been given in Pascal, because 1 atmosphere pressure, 1 atmosphere means 101,325 Pascal. So it has been given in Pascal. So all the information has been given in SI unit from the Aspen Plus to Excel, Microsoft Excel. And Microsoft Excel also has got the Aspen Plus output. that is product up and product down. It knows these are the two units. So Aspen Plus is able to send these two information over there and feed information to MS Excel. So we are able to send the data from Aspen Plus to Microsoft Excel. Now the reverse has to be done. Then our job will be completed. For that, let us go back to Excel. Now we have to send the data back to Aspen Plus because we will do the calculation in Microsoft Excel. We will write the code in Microsoft Excel, right? So suppose we have to divide the feed into 3:7 ratio and put it in product up and product down. Then each of the component, that is ethanol and water, both will be divided into 3:7 ratio. In other words, the product up, ethanol, will be 0.3 multiplied by the feed ethanol. So what we will do, we will write over here is equal to Aspen input of ethanol multiplied by the real parameters 0.3. So all the real parameters are over here. We have defined, you remember? We have defined over here the real parameters. What are they? Three real parameters we have defined, 0.3, 4 and 9.5. So these real parameters have been sent to Microsoft Excel, 0.3, 4 and 9.5. So we have defined the output as Aspen input B2 into Aspen real parameters B2. So this is 0.008333. Okay. So Aspen input B2 multiplied by real parameter 0.3. So if 30% goes to product up, then 70% will go to product down. So we will write a code that is Aspen input of this multiplied by 1 minus real parameter. Okay. Similarly, water. Water will be Aspen input of water multiplied by the real parameter. And this one will be 70%, that is 1 minus real parameter of 0.3. So this will be water multiplied by 1 minus the real parameter. Okay. And what will be the total flow? Total flow will be ethanol plus water. And this will also be ethanol plus water. Okay. That is how it is done. Now, temperature. What are the temperature? For temperature, there is no equation. Temperature is, as we remember, the temperature is 51 degrees centigrade and 86 degrees centigrade respectively. So we will directly put those as 51 degrees centigrade, but we have to give it in Kelvin. So 273.15. And this one will be 86 plus 273.15. So this is the Kelvin. Pressure. Pressure is, what is the pressure of product up? You remember it is 4 atmosphere and product down is 9.5 bar. So we'll write over here is equal to 4 atmosphere. So 4 multiplied, not 4, we will use it as a real parameter because we have the option to change. So real parameters multiplied by atmosphere 2 Pascal. So 101325. And the other one is 9.5 bar. So it will be the other real parameter 9.5 bar multiplied by 1E5 because it is bar. So bar 2 Pascal is multiplied by 1E5. Okay. So that's what our complete model equations are. At this moment, we have this information. We have defined everything in Microsoft Excel. We have not defined this equation in Aspen Plus. Now let us rewind and run it once again. Run it and then check. Now results are available without any warning. Just check the results. Stream 86 degree centigrade, 51 degree centigrade. Okay. So product up is 30% of 100 kilomole per hour. Product down is 70. So 3:7 ratio. This is also 3:7 ratio. Now those things we have not defined in Aspen Plus. Those things we have defined in Microsoft Excel. But Microsoft Excel and Aspen Plus, they talk to each other very nicely and they have exchanged their data. Aspen Plus has given the feed data to Microsoft Excel and Microsoft Excel has calculated in their way that we have defined in Microsoft Excel and it has sent back the data to Aspen Plus. That's how the entire situation has been defined in a proper manner. Okay. Now let us change them. So let us now go to the feed input. Instead of 200, let us make it 300. Okay. So I am not changing anything other than this. And let us see how the results differ. So we have changed this and we are running. And check the results, stream results once again. It has automatically changed. See, again it is 3:7 ratio. Okay. But product up and product down, everything is being calculated in Microsoft Excel. You see, this is 90, right? Because it has taken the input from B3. What is B3? B3 is now this one. This one is equal to this multiplied by 3600. It is 300. Just whatever we have given over here in the feed. Feed we have given as 300. So this information has been given in the water data and this data is again being calculated over here. Okay. So this multiplied by 3600 is equal to 210. Product down 210 and that is being reflected over here in the stream. We are finding is over 210 over here. Okay. So that's how the changes are done. Now let us try to change something else. For that, let us go to the block B1, the setup, and we will change the pressure from 4 atmosphere to say 5 atmosphere. Okay. And see, now it is 5 atmosphere. So all the calculation is being done in Microsoft Excel. You just check, it has come to be 5 atmosphere because Aspen input has been changed to, the real parameter has been changed to 5 atmosphere over here. So that's how we work with Microsoft Excel and Aspen Plus in combination, right? So we have defined how this thing can be done. Okay.